Pop quiz. In carbon-13 NMR, which statement is true? A, you always see proton splitting. B, the signals are weak, so we average many scans. Or C, the shifts are measured in hertz. Hold your answer. We will reveal it in a moment. In this video, you will learn what carbon-13 NMR measures, why most peaks appear as singlets, and how Fourier transform methods let us record useful spectra in seconds. Here's the bigger picture. Nuclear magnetic resonance works for any nucleus with spin. Proton NMR watches hydrogen. Carbon-13 NMR watches the carbon-13 isotope. The principles are the same, but the details look different. Only about 1% of carbon atoms are carbon-13. In a single molecule, that is easy to miss. But in a macroscopic sample, there are still trillions of carbon-13 atoms at every distinct position. That is enough to build a spectrum. Carbon-13 chemical shifts span a wide window from near zero up to around 220 parts per million. Carbonyl carbons sit far downfield. Aromatic and alkene carbons live above 100. Carbons bonded to oxygen or halogens often appear around 50 to 90, and simple alkyl carbons cluster below 50. Try a quick example with ethyl acetate. Count unique carbons, then place them. The carbonyl shows far downfield. The methylene next to oxygen sits near 60. The two methyl groups land in the alkyl region at different positions because their environments are not the same. One molecule, 4 signals. Students often ask, where are the splitting patterns? First, 2 carbon-13 atoms rarely sit next to each other. So carbon-13 to carbon-13 coupling is extremely unlikely. Second, we record these spectra with broadband proton decoupling. A second radio signal makes the protons flip so rapidly that their magnetic effects average to 0. The result is clean singlets for each distinct carbon. Hence, your pop quiz answer was B. The signals are weak, so we average many scans. Because carbon-13 is rare, the raw signal is small compared to electronic noise. We collect many scans and average them so that random noise cancels while the true signal adds up. That is the idea behind signal averaging. Fourier transform NMR makes this fast. One short pulse excites all the carbons at once. The instrument records a time signal called a free induction decay. A Fourier transform converts that time signal into the frequency spectrum you read. With digital averaging, you can gather a usable carbon-13 spectrum in seconds. So far, you have learned the wide shift window, why lines are singlets with proton decoupling, and how signal averaging with a Fourier transform brings out weak signals. Want to lock this in? Your personalized practice test and flashcard set are all waiting for you. Tap the link and give yourself a quick check. Now, let's explore symmetry. In tert-butyl chloride, all 3 methyl groups are equivalent, so their 3 carbons give one line. The central carbon gives another line. Symmetry can collapse many carbons into a small number of signals. Reading a carbon-13 spectrum starts with counting unique carbons, then classifying by region. A downfield line suggests a carbonyl. Lines between 100 and 160 hint at aromatic or alkene carbons. Lines near 60 often mean a carbon attached to oxygen. The low field side of the alkyl region often points to carbons next to halogens. Here are 3 quick pitfalls to watch out for. First, do not treat line heights as a head count. In routine decoupled carbon spectra, intensities are not proportional. Second, quaternary carbons can look faint because they relax slowly. Third, remember that decoupled spectra hide proton splitting by design. Here's a step-by-step guide to help you. 1. Count the distinct lines to estimate how many unique carbons the molecule has. 2. Match lines to likely groups using the shift regions. 3. Use symmetry to explain why some carbons might be equivalent. That sequence takes you from a forest of lines to a sketched structure. To recap, Carbon-13 NMR reports one line per unique carbon across a wide parts per million window. Lines are usually singlets because we use proton decoupling, and carbon-13 neighbors are rare. Weak signals become readable thanks to signal averaging and a Fourier transform. Ready to quiz yourself with the content covered in this video? Check out the link in the description where you'll find Quizlet content made just for you.